VRAM sure has been a hot topic lately, huh? Whether you're comparing GPUs from last generation to this generation or from manufacturer to manufacturer, there are a lot of questions out there about how it's implemented and what's needed. Like, how much VRAM is necessary? How does bandwidth play a role? And what happens if you run out? By the end of this video, you'll have a better understanding of just what affects the VRAM capacity, and it's more than just memory modules. Now before we get into the memory itself, what does VRAM even do? The essential function of VRAM is to hold the data that the graphics card will be using for rendering out to the display. So everything in a game scene you're seeing will need to be in memory before it can be shown, especially the textures. This is why generally the higher the pixel count, the more memory you'll need. Why is GDDR different from DDR memory you find in your computer? Well, the simple answer is, well, they're very similar. But GDDR is built for graphics cards and has a much higher bandwidth optimization. Well, how is VRAM performance determined by the graphics card? Well, you can just throw more DRAM into a system and that just kind of works. Why is it that simple for GPUs? Well, it comes down to the GPU memory bus interface. This is the bridge between the GPU core itself and the memory dies, which is called the bus width, and can be compared to a highway. The more narrow the highway, like a 2-lane, the less data can travel in a single pass. Widen that to 8 lanes, and now significantly more data can get through. You'll typically see the bus width range from around 128-bit to a 384-bit on the last generation of graphics cards. So the wider the memory bus, the more memory I get. Awesome! Well, hold up. Not done yet. The other part of the equation comes in the receiving end. The memory module capacity is the destination of that highway, and it's where that data gets stored before retrieval. Just like desktop and laptop memory, you have memory modules that come in various sizes, which are typically in 1GB or 2GB modules each. This is why some graphics cards will have a larger number of memory modules despite having less VRAM capacity. It's a combination of the memory bus and memory module capacity that determines performance. Basically, each memory module will consume 32 bits of the bus, because each memory module operates on that bit level. Now you can probably start to see how this plays out. A simple example is the RTX 4060 Ti, which is a 128-bit bus, and by simple math, you can fit 4 32-bit modules within that bus. That left NVIDIA with the decision of which modules to use. If the company had gone with 1GB modules, then the RTX 4060 Ti would have been a 4GB card. But they instead went for 2GB modules, resulting in an 8GB card. See how that works? But Keith, there's a 16GB version of the RTX 4060 Ti. I know. And remember whenever I said typically 1 or 2GB modules? Yeah, that card is using 4GB memory modules. But the memory bus is the same 128-bit, meaning the destination got larger, but not the highway itself. There's more to it than raw capacity, and the benefit between 8GB and 16GB version is, well, minimal for gaming, as reviews have shown. See, the bus width size and the memory module capacity matter a lot, but it's their relationship that is most important. The bandwidth between these two is absolutely crucial. In some reviews, we saw the performance of the last generation RTX 3060 Ti match or beat the RTX 4060 Ti when moving to higher resolutions. Now this was because the RTX 3060 Ti runs a much wider 256-bit memory bus. Even though the capacity was the same, the wider bus allowed for higher memory bandwidth and usually better performance. Call back to the highway analogy, and the RTX 3060 Ti basically has more lanes to get more data between the GPU core and the memory modules faster. That's of course typically, but not always. Now that we laid out the configurations, you may be wondering, how much VRAM do I need? If you ask the internet, the general answer is all of it. But in reality, there are general guidelines you can follow for now if you're gaming at a typical resolution. Here's a good starting place for high settings gameplay if your GPU itself is up to snuff. 1080p gamers should be well served by 8GB of VRAM. 1440p gamers should consider no less than 12 gigabytes of VRAM, and 1440p ultra-wide to 4K would do well to have 16 gigabytes or more. Of course, there's no harm in having an abundance of VRAM, but it doesn't always make things better. If you're considering future-proofing, then obviously you'll want to overshoot these recommendations, and that might get you more legs on your GPU. So buy a 4K target card with 16 gigabytes or more of VRAM for 1440p today, and you'll certainly get a longer life out of it. Now, if a card comes in two options, say an 8GB and a 16GB variant, then I almost always suggest the higher variant unless the price doesn't make sense. Unfortunately, that's not a common practice for GPU makers lately. And typically, AMD graphics cards have offered higher VRAM capacity and bus width compared to NVIDIA at the dollar prices that they compete in, so be sure to check out the independent reviews and make your own determination for how much you want for your gaming needs. Now that you have a general guideline and an idea for speccing out your rig, what happens if you have enough for today and find yourself saturating that pool of VRAM later? Well, if you do have to give it the beans a little too hard, then you're likely going to experience some horrible frame pacing and stuttering while your gaming system starts swapping VRAM information to and from the much slower DRAM in your motherboard. If you find this to be the case, then you're going to want to reduce memory-intensive settings to lower the demand back into your real VRAM buffer space. This is what I've had to do to be able to enjoy Baldur's Gate 3 on the go with my laptop's wimpy GTX 1650. But something to consider is that often a GPU is paired with the memory capacity that it can comfortably manage. That mobile GTX 1650 wouldn't get any faster with 16 gigabytes of VRAM because it just doesn't have the grunt to handle it, especially with the settings that you would run to use so much VRAM. So while more VRAM is nice, doesn't always mean it'll matter. By now, you should have a better understanding of VRAM in general from what it does, how it's configured on your graphics card, and how much you might need, and what happens if you don't have enough. I hope you all learned something today and can feel a little more confident when shopping for your next graphics card upgrade. And if it's your first PC build, then congratulations and welcome to the party. And that'll do it for this one, so make sure you're subscribed and ring that bell so you don't miss upcoming PC hardware and software goodness.